All right, pre-calculus. Hope this morning's review will help. Yeah, whether you're chiming in live or watching this later on, I have some questions from the lab that I want to go over. That was going to review stuff, and then try to work a mix of problems here, getting ready for the exam on all of the trig stuff. So trig equations, trig identities. There's a lot of different ways to ask questions involving this stuff. There's a lot of identities, formulas involved, and you have to recognize when they're going to be useful. So working enough problems to be able to recognize what you're looking at and what kind of formula would be useful on that and how to get where you need to go. A lot of variety on this. So I want to try to work a variety of practice problems. We had a bunch in the lab. And certainly chime in if you have questions or particular topics you want to look at some more. I guess started with some that people were asking about from the lab. So let me get situated for that. All right, so I don't think these will be readable off from the lab paper, but I'm going to write down what these problems were and work through them as examples of this sort of thing. So maybe I'll do a couple of this type of problem. 14 and 15 on the lab look similar, but are different types of problems. So I'll work the lab ones, but I'll also work some similar questions, maybe out of the book here. So if you look at number 14 on the lab, it's asking for the exact value of inverse cosine of 7 pi over 6. Couple of different ways we could go about this, because we do know some exact values about stuff involving pi over 6, but I also want to think more generally about this kind of problem. When you have inverse trig of trig function. This situation, inverse trig function of something. So now it seems like those would undo each other, especially when it's the same function, right? This is inverse cosine and cosine. Shouldn't you just get the same thing back? Well, that's only true when you're talking about one-to-one functions. So for trig stuff, there's a little piece of the domain where cosine is one-to-one. Basically from minus pi over 2 to pi over 2, that would work perfectly, and you'd get the same thing back if you do inverse cosine of cosine. Outside of that, you get something different. You have to think this thing through differently, because once you're not talking about a one-to-one function anymore, it's not that predictable how the inverse is going to work. We're going to have to work through this. This is a unit circle kind of problem. So if you see inverse trig of something, it's a good place to apply your unit circle knowledge and think this through. It's a quadrant question as much as anything. So if you think about it the right way, that's unit circle picture. And we're going to see that when you have trig function of inverse trig function, that's more of a triangle picture. So it's different pictures involved, and we want to sort these things out. There was a couple of these in the homework also. See how that turned out. But this one, I'm going to do the picture of it, but I want to think about what we know here also. 7 pi over 6. Is a little bit more than pi. This is pi. 7/6 pi is pi plus pi over 6. So that would be down here. The cosine of that would be the cosine, would be the negative of that, right? So cosine of pi over 6. I'm starting to write small, and I'm trying to break that habit. But my picture here says cosine of pi over 6. That's one of the nice exact values that we know. Cosine of pi over 6 is square root of 3 over 2. So this one's just going to be the negative of that because I'm in third quadrant where cosine is negative. Inverse cosine of that is asking the question, where does cosine come out to negative square root of 3 over 2? this is actually second quadrant answer. It's going to come back with a second quadrant value of that 5 pi over 6 is the trig value where you get negative square root of 3 over 2. On the unit circle, you can kind of picture what's happening here in that inverse cosine takes the value and gives you the angle in the first or second quadrant that goes with it. Cosine takes the angle and gives you the x value on the unit circle. So cosine of 7 pi over 6 takes this angle, 7 pi over 6, and gives you the x value right here. That's our negative square root of 3 over 2. Inverse cosine takes that x value, and it always goes up. Your x value has to be between minus 1 and 1, and it always goes up to the first or second quadrant angle for it. So that's actually the second quadrant version of this, or the corresponding angle in the second quadrant, which is 5 pi over 6. That one can be verified in a calculator. Some of you like calculators. I'm not that into that. But we're understanding those functions the same way the calculator is, that it's limited to those quadrants. The inverse cosine is limited to those quadrants. So first of all, I better have this in radian mode for it. And I've been using this in another class. So I'm going to remember how to change my mode here to radians. Yeah, now radian mode. If you do inverse cosine of 7 times pi over 6, I get this number. Might not look too familiar to you, but you can check that the exact value there is 5 pi over 6. Should be the same thing. Not even close to the same thing. Parentheses. Let me try that again with parentheses in the right place. Most of your calculators, when you enter one of these kind of functions, it's going to come up with an open parentheses because this is a function of. I think that's a very good idea because we have to be careful about what's inside the functions and what's not. I think I got my order of operations messed up. Let me try to get this readable. But inverse cosine of 7 times pi divided by 6, all inside of there is, the same as what 5 times pi divided by 6 came out to. So that was right. The first time I entered it without parentheses, I messed up that order of operations. So that's a risk right there. What the calculator actually did in this one was the inverse cosine of 7. And then it took that and multiplied it by pi and divided by 6, which is completely different from what I wanted to do. Right? So you have to be careful about your inputs. And if you have TI calculator, the trig and inverse trig functions are going to put that opening parentheses as part of the function. And that's actually very useful because you have to be careful about where you close that parentheses up. All right, that was a nice way to verify that came out right. Picture should hopefully make some sense to you there, that it's going to lean toward these certain quadrants. Inverse cosine always takes something between minus 1 and 1 that's an x value, and it goes up to your first or second quadrant angle. The other inverse trig functions, if you're doing inverse sine, that starts with a y value between minus 1 and 1, and it gives you an angle over here in the fourth or first quadrant from minus pi over 2 to pi over 2. So you'll end up always in the first or fourth quadrant with your answers to that. So let me do another similar one there before we go to the other type of problem. I'm going to take one out of the book that's inverse trig of trig function of something. I'm going to do number 45. It's right next to the homework problems, but it's slightly different. But we're starting with this kind of problem. Find the exact value of any of each composite function. That's inverse trig of trig. It's the same function, but it doesn't give you the same thing back if you're in some weird quadrant. And 4 pi over 5, I don't know exact values for 4 pi over 5. But I can still use the unit circle kind of picture to see where that ends up. So I have to think about this picture-wise. We'll verify using calculator. But on the unit circle, this is pi. So that's 5 pi over 5. If I split this into fifths, that would be like this somehow. 1, 2, 3, 4, 5 pi over 5. You could do this in degrees, but I don't think 4 pi over 5 is going to be most of the way there. It's going to be somewhere out here. So the tangent doesn't give you the x or the y. The tangent gives you the slope of this thing. The tangent of 4 pi over 5 is the slope. And the inverse tangent is going to take that slope and give you back something in the fourth or the first quadrant. Inverse tangent works in quadrant 4 and 1. So it's going to take that slope and give you the corresponding angle in this quadrant that has that same slope to it. So what would this be? If that's 1/5 of pi from here, then that's 1/5 of pi from here. We'd be at minus pi over 5. We can work that out on a picture. Let's verify that with calculator. I'm going to do this a step at a time on this one instead of doing the composition. First thing that happened there was tangent of 4 pi over 5. 4 times pi divided by 5. You should get this. That's the slope of that line, actually, is negative 0.7 something. The inverse tangent of a negative slope. So the inverse tangent of that answer should give you that negative value. Inverse tangent of a negative comes out negative. That's a fourth quadrant. Negative 0.628 something. Let's check that. We think that's supposed to be the same based on our picture there as negative pi over 5. And sure enough, that's the same value there. That's good. So they can be verified by the calculator, but if you didn't know what that was, you might not recognize that value as an exact one. So the picture tells you the exact value there nicely. Understanding unit circle trig is the nicest way to go on that kind of problem. On the other hand, and this is a very different approach, what if we have the other way around? Trig function of inverse trig function of something. That's going to be a different situation. That's going to be more of a triangle problem. And this, I just worked through a problem in Calc 3 that involved rewriting things this way. So I know these show up ultimately in calculus when you're doing substitutions and stuff there. But we're just going to be able to rewrite this expression. And for this kind of problem, they don't have to be the same function. We can have like cosine of inverse tangent of 2/3. This one's not from the book. I just made that up. That's an example of trig of inverse trig. Similar to some of these in the book and similar to number 15 in the lab, which we're going to come back to now. But anytime I have trig of inverse trig, I can think of this in a triangle. This is an angle. The inverse tangent of something is an angle. And if I draw a triangle with that angle in it, this is my angle in a right triangle. And the inverse tangent of 2/3 is the angle that has opposite over adjacent as 2/3. So tangent is opposite over adjacent. The tangent of this angle is equal to 2/3. That's opposite over adjacent. So your regular SOHCAHTOA stuff can help set that up. This is the angle that we're talking about. So the cosine of this angle would be adjacent over hypotenuse. And that's going to be my answer to this is what is adjacent over hypotenuse for this one. The only thing is, I don't know what the hypotenuse is, right? But I know Pythagorean theorem. So if I got these two sides, I can get the third side. Hypotenuse there is the square root of 2 squared plus 3 squared. Radical 13 is what that comes out to. So this is square root of 13. And my answer then is adjacent over hypotenuse 3 over square root of 13. Or if you rationalize the denominator there, 3 radical 13 over 13. So those can all be done with a little right triangle. I don't even try to draw it nicely or anything, but just understanding the two sides that you're sort of given and figuring the third side. And then remembering your SOHCAHTOA stuff, you can work your way through any of those. Let me do the one from the lab. I'll put one side by side with this. We'll have the same kind of steps. Number 15 on the lab was this way around. It was a cosine of so that's pretty similar to the one that I just made up. This one, if you're super good with your exact values, you might recognize what angle that is because we had an angle in our exact values that the tangent of it came out to square root of 3 over 3. But I don't need to know what the angle is. I need the cosine of the angle, and I can work it with the triangle just like this one. Look at your inverse trig function. Which one is that? This is saying, well, tangent's opposite over adjacent. So use this as opposite and adjacent. If everything's positive, that's good. Square root of 3 over 3. These could be negative sometimes, one of them, but this is both positive. Pythagorean theorem tells you the third side. This is going to be 3 squared plus square root of 3 squared. So that's 9 plus 3 is 12. So the hypotenuse is the square root of 12. I can simplify that some. Those are the three sides. This is the angle I'm talking about. This is the angle inverse tangent of that. The cosine is adjacent over hypotenuse. So 3 over 2 radical 3. Or 3 radical 3 over 6. Square root of 3 over 2. So if you recognize that as a 30-degree angle or pi over 6, that's great. That is your 30, 60, 90 triangle, sort of. But it is. And the cosine is square root of 3 over 2. But you don't have to recognize it. You don't have to know any exact values of the angle itself. You just go work with the sides of the triangle. That'll work.
Okay. I will say that we do have some, like Taylor has an air section.
That's the basic kind of problem we want to be able to do on that is trig of inverse trig of something. So let me work one with some different angle, different functions involved in it. You could have some weird ones. And I don't see one right now in a book. I'm going to tackle one more on this while we're on the subject. What if I have...
I haven't taken his test this morning, but for the other section, sometimes it looks like
sine of inverse cosecant of
not that, but
4.
my son does. So it's not exactly.
That doesn't look like a fraction now, but we can think of it as a fraction. You want to think of it as a fraction to use this process. The cosecant is reciprocal of sine. Sine is opposite over hypotenuse, so cosecant is hypotenuse over opposite. So I want to think of the 4 as 4 over 1, and I want to draw my triangle. I'm not even going to try to draw it to scale, but hypotenuse is 4 and opposite is 1. This is my angle. That's the inverse cosecant of 4 over 1. I can figure out the third side because 4 squared equals 1 squared plus this squared. So I got 15 Squared radical 15. And the sine of this angle, well, sine is actually just opposite over hypotenuse. So I don't even need that third side after all. I just have 1 over 4. So I could do any function of it once I have the triangle drawn. This one came out nice because sine and cosecant are reciprocals. That's fine. Now you don't have a cosecant inverse button. That would really be a pain to do anything with that in the calculator. So triangle works nicely for that. Number 16 on the lab, I also had questions about it. It involves some of the simplification right there. So 16 this is to simplify. And it looks like well, it doesn't look like any obvious simplification that needs to be done. So we got to think this through. It looks like a bunch of different functions involved. Without going trigonometric yet, just think about it algebraically. What's happening here? I got a fraction plus a, well, tangent's really a fraction also. If I want to break things down into sine and cosine, that's always a good start. And then I'm going to have fraction plus fraction. And I know how to do fraction plus fraction using common denominator stuff. So I'm going to think this thing through that way. I got cosine theta over 1 plus sine theta. And I got tangent, which is sine over cosine. I'm going to get a common denominator and add them together. Just doing the algebra, what your algebra would tell you to do on this, which is I got 2 different denominators, so I need the common denominator that includes them both. This is going to be over those 2 factors. Cosine theta and 1 plus sine theta is my common denominator. So this is being multiplied on the top and bottom by cosine theta. So I got cosine squared theta. This is being multiplied on the top and bottom by 1 plus sine theta. And I have to multiply that out. So that's plus sine theta plus sine squared theta. That's just doing what algebra tells you to do on that, as if I just had 2 letters in there. But they are trigonometric things, and here's where I use a little trig. Hopefully, it occurs to you looking at that a couple of these signs are the nice ones. Cosine squared plus sine squared equals 1. So that's going to simplify a lot. To 1 plus sine theta. And that's one of the nice things to look at. You put things in terms of sine and cosine, and you're trying to get situations where sine squared and cosine squared are added together like that. That simplifies things a lot. And then the algebra, again, since that happened to match with our factor on the bottom, we just simplify to 1 over cosine theta. Or if you want, you can write it as just secant. That's what that comes down to. So it simplifies to just the secant function. So that's the kind of simplifying that happens in equations a little bit, and it happens a lot with verifying identities where you have to rewrite stuff like that. A lot of it's just doing algebraic stuff, the kind of steps that algebra simplifying teaches you to do, and then applying some trig stuff when you run into it. Really, the only trigonometric fact we had in all that was the sine squared plus cosine squared equals 1. The rest of that was just algebraic simplifying with funny looking symbols. So get some practice with that. That's what you need in verifying identity problems.
All right. No, you haven't got, you did the iPad, right?
All right, using these other identities, when we have something where there's different stuff there. where there's different arguments, different inputs into the trig functions, and we have to think that through a little bit. So let me work through one of these identities from the homework where there's a different input that shows up. This is actually one of the problems from 7.5, number 62. We're trying to establish the identity or verify the identity, the sine of alpha plus beta over cosine alpha cosine beta is supposed to equal tangent alpha plus tangent beta. Whoa. Okay, so if it's a verify the identity problem, so I'm looking at which side is more complicated that sort of gives me something to do. I want to park one of these sides as the destination that I'm going to end up at, and I want to start doing some stuff on one side. Now, this is pretty simple already and doesn't really suggest a whole lot of stuff to do. So I'm just going to park that. I know I want this thing to end up looking like that. I'm going to start doing some stuff here. The more complicated side usually. And what's complicated about this is that there's a different input. This stuff is in terms of alpha and beta is the inputs. And this has the sum in there. I don't want a different input involved. I want to break that down using whatever identity applies to that to change that input. So this is where you use your double angle, half angle, angle sum properties, stuff like that. This is an angle sum, obviously. So I have an identity for what sine of alpha plus beta is. If you don't have all those memorized, that's kind of okay the way this is going, but we're going to use some of these identities that are summarized at the end of the chapter. But the sine angle sum property for sine is going to be a plus with the functions kind of mixed around. So it's sine alpha cosine beta plus cosine alpha sine beta. And I still got my denominator here. I'm not working with that. Yeah, but now I've got that all broken down into the same inputs. That's the first thing that really needs to be taken care of in an equation or identity. If there's different inputs, you got to break that down first using whatever formula applies. Now I'm just going to do algebra on it. I have two things over the denominator. I'm going to separate that out and see if I can simplify stuff. So doing what algebra tells me to do, I'm going to be able to simplify these fractions a little bit. So it's division by a single term. So I break it up into separate fractions and try to simplify where there's common factors. And sure enough, some of it simplifies out. Cosine beta cancels. Cosine alpha cancels. We have to be able to have the same inputs to do that sort of thing. And then what I'm left with, that's sine alpha over cosine alpha, so that is tangent. And this is sine over cosine also, so that's tangent beta. That's exactly where I was supposed to end up. So mostly algebra after the angle sum property gets used. And that's typical with those. If you have an identity or an equation where there's different inputs, resolve that first and then do what the algebra tells you to do on it. I had a variety of problems on these things, and do work enough of them where it starts to, you start to pick up on some of these patterns. But that's technical. Same kind of thing on 19. I'm looking at the practice lab now, and number 19 is similar kind of situation. Another identity, but it starts with cosine of x plus pi over 2 is equal to negative sine x. Now you can see that on the graph if you're good with your what's that, phase shift and whatnot. You could look at this on the graph and see that they look the same. But to really establish the identity, we need to rewrite one of these using what we know and get it to end up as the other. There isn't anything to do here, so I'm going to park that one as my destination, and I'm going to do what I have to do here. I have a different input here. I want stuff just in terms of x, so this is another angle sum. I got to break that down. This is the angle sum property for cosine, which ends up with a minus in there. It's cosine, cosine, minus sine, sine. So that's cosine x, cosine pi over 2, minus sine x, sine pi over 2. That's how you break down an angle sum using cosine. I still on the screen. And then, well, I do some algebra here, but it's not really algebra. It's the pi over 2. I know the values of. So what goes in? Pi over 2 is, you're on the unit circle, cosine is 0. And sine of pi over 2 is 1. So those are going to come out nice. I have cosine x times 0. Minus sine x times 1. So that's 0 minus sine x. I got negative sine x. That's exactly where I'm supposed to end up. So the nice thing about identity problems is you know where you're supposed to end up. You just got to get there, applying what you know to the situation on the more complicated side, and working it out until you can get it to look like the other side. That's the deal with it. That's the beginning of really how mathematics works at the more abstract level. You make an observation, and in these problems, the observation is given to you that those look like they're the same thing. And then you have to use what you know to verify that those really are the same thing. There's a ton of that sort of pattern recognition in mathematics, where you look at a situation, figure out what it might be, what you think is probably true about your situation, and then you have to use known facts and information to verify that or prove that. We're doing that all the time as you go further along in math. If you're taking more pure math instead of applied math, which some of you might be headed that direction. I don't know. That covers the questions that I had come in on this. I got a little time left. I feel like I should do some equations because we talked about the equations that much. So let me look at chapter review stuff. Think about solving equations on this. All the solutions between 0 and 2 pi. We do this. I'm going to do 2 of these. I'm just taking them from chapter 7 review. Nothing terribly fancy here, but a couple of solve the equations problems. I'll write them both down and we'll work with these one at a time. Number 68 and 70 from the chapter review. Just trying to get some practice with how these work in equations. So I'm trying to find the theta that makes this thing true. And in the instructions, it says find theta between 0 and 2 pi. So we're not looking for big, huge list of stuff. We're just looking for the these values between 0 and 2 pi, regular unit circle picture. Where is this true? Between 0 and 2 pi. And that's typical with the equations. We'll get the ones between 0 and 2 pi, and the rest of them are just repeats of that periodic functions. So looking at both of these for a minute right here, you notice this just has one function in it. This has 2 functions, and they're different inputs. You see the different inputs there. That's something I'm going to have to resolve. You can't mess with different inputs. You got to rewrite that to get them in terms of the same thing. So I have a double angle identity I'm going to have to use there to rewrite that in terms of functions of theta to get things down to functions of the same thing. 68, I don't have to worry about that. I only have one function going on. The other thing I like to do is put things in terms of sine and cosine. I don't know that much about secant. Okay, if I stop and think, I know a lot about secant, but you probably don't know that much about secant. And we're not as familiar with that, and we don't have to keep secants around right now because we can put stuff in terms of cosine. The one thing to remember about secant is it's the reciprocal of cosine. This is still squared, so the reciprocal of cosine, if I square that, it's still squared. Now, do what your algebra teacher would tell you to do. If you can remember what your algebra teacher said about anything. One of them was, if there's denominators in an equation, multiply and get rid of the denominators. So I'm going to multiply by cosines, or you could call this cross multiplying here. It sort of is. So get rid of the most complicated thing in the equation, which is getting rid of the denominators there. Now I'm going to try to get theta by itself. So get rid of the 4. I got to get rid of next. I don't have an inverse for cosine squared. I have to take care of that squared first. So I'm going to take care of the squared now. This is your regular square root property. We're just talking about this in algebra. Square root of both sides, you remember your plus or minus. I hope the square root of a quarter. That comes out nice. So cosine theta is plus or minus 1/2. And we know where theta is equal to positive 1/2, and we know where theta is equal to negative 1/2. Or do we? We know that. We know that on the unit circle, so I'm thinking about this. On the unit circle, cosine is 1/2 up here and down here. So I get positive 1/2 at pi over 3 and minus pi over 3. I don't want to call it minus pi over 3 because I'm trying to do from 0 around to 2 pi. So that's pi over 3. 2, 3, 4, 5 pi over 3 is my name for that one. Between 0 and 2 pi. And then, where's cosine equal to negative 1/2? That's the corresponding ones over here. It's negative 1/2 at 2 pi over 3 and 4 pi over 3. And that's the full list between 0 and 2 pi. That's the full list of solutions. They're out of order, but those are the 4 places where this is true between 0 and 2 pi. Now, if you know some stuff about your graphs, that's good. Secant, if I look at secant between 0 and 2 pi, I'm trying to do review, so I'm going to think a little bit about graphs here because it's nice to tie this together and think about the graphs. Graph of cosine looks like this, roughly, right? This is pi is where it's at the bottom. Graph of secant then would be one of these turned upside inside out this way. It has this and this and this. That would be your secant graph. Secant squared is always going to be positive. So if I square something that looks like that, the graph of secant squared would go up to infinity. This would be positive, and then it would be like this again to get to 2 pi, the x-axis. We'd have a couple of those asymptotes in there where cosine is equal to 0. Where is this? This is 1. Where is secant squared equal to 4? Should happen at 4 different places across that interval, right? 2 right there and 2 right there. That's pi over 3 and 2 pi over 3, and 4 and 5 pi over 3 next to that one. So being able to graph these things is nice if you can think about the graph. Or, of course, take a minute. You can put that into the calculator and see where it's equal to 4 and see how many solutions are there. If you wanted decimals, you could get them off from the graph. You can at least see that that makes sense with what we ended up with there. So that's nice to do if you have time. But these are time-consuming problems. Now, 70. I mentioned on this one, we have 2 different inputs into the trig functions here. That's not good. We want to resolve that first. So sine of 2 theta, how do we put that in terms of other stuff? And your double angle property for sine is the angle sum had functions mixed around. Sine 2 theta is 2 sine theta cosine theta. I have to stop and think about these things because I don't use that all the time. And if you have to look it up, that's okay. You just have to look at this and recognize there is one. And then you know where to find it. You look it up. You got this formula. The more you use them, the more you're going to remember them. Your calculus teacher is going to think you ought to know all of these things by heart when you go into calculus. Your calculus teacher is realistic to know that's a little bit wishful thinking. But the more you use them, the more you know them. So by the time you're pushing through calculus, hopefully they're all burned in pretty well. But sine 2 theta is 2 sine theta cosine theta. That's the trig part. Now we think algebra. What does algebra tell you to do with that kind of thing? And I don't know how much algebra tells you, but think about what's going on here. We got a 0. We're trying to factor. We got a common factor. So trying to solve for something's equal to 0, you hope you can factor it. We got a common factor of sine that we can factor out. So write in factored form, use your 0 factor property. Factor out the sine, I got 1 plus 2 cosine theta. 0 factor property says if that's true, then either sine theta is equal to 0 or 1 plus 2 cosine theta is equal to 0. That's ready to go on a unit circle now. Where is that true? Sine's equal to 0 at these 2 points, 0 and pi. And this, well, this isn't quite ready yet. Solve for cosine now. Cosine theta is equal to negative 1/2. That was this picture. We already did this on the unit circle part, and we found that was true at 2 pi over 3 and 4 pi over 3. So those are all solutions to that equation. You can plug stuff in and make sure it works in an equation. Graph of something like that would be a little crazy, so I don't want to think about the graph really there with the 2 different inputs. But those are all solutions to that between 0 and 2 pi. All right, a lot of variety of problems to do on this. The practice stuff had a good mix of them. That one kind of similar to what you end up doing on 23, 24 there. From the practice. So and again, low on time here. I left that list of topics in Monday's announcement. So I'm reading that right now. It says exact values, unit circle trig, trig graphs, trig equations, and trig identities. That's good coverage of the different stuff. There's a lot of ways to ask questions on that. What we've talked about, all of those things in this brief little review session. Not much with the graphs, but a little bit with the graphs there. You want to get some practice on each of those things, and with a longer time span and open book testing like we're doing now, this is a lot more of a problem solving kind of thing. So there's going to be a variety of problems, and you've got a little time to think them through and figure out what facts you need and how to approach it. You just want the basic patterns there where you know what type of problem this is. Am I dealing with an identity or an equation? Is there separate inputs to deal with? These kind of pattern questions that help you narrow down the types of stuff that we ask. The neat thing about trigonometric functions is there's so many ways to rewrite things. That's what becomes a major tool in calculus, where even functions that don't have anything to do with trigonometry, we're going to turn them into trigonometric things because there's all these nice identities and ways to rewrite things. So the better you are with these patterns, the more smooth sailing that's going to be if you do go on and take a calculus sequence of things. Being able to rewrite them in that form and then manipulate them using these identities and stuff, it's very powerful when you get the hang of it. So I hope this is a good start for you on that. It has potential to be very helpful down the road. We'll wrap this up for now. certainly welcome to get some more questions to me to ask. Some more questions between now and then. I need to hear from most of you about when you're going to take this test. So let me know Thursday evening, and then Friday morning or afternoon times there. So drop me a note. Let me know what time you want to take the test. I'll be getting those together. And let me know if there's any questions. Get those out soon.